Then our next presentation is online, and the speaker will be available to take questions after the video. So go ahead.
Hello, this is Takuya Nakashima from the University of Tokyo. The title of this presentation is Model-Based Design and Safety Assessment for Crewless Autonomous Vessel. This research was supported by the Nippon Foundation's Joint Technological Development Program for the development of unmanned ships, so-called Meguri 2040. The Designing of the Future of Full Autonomous Ships DFAS project was launched on February 2020. This project aims to realize crewless maritime autonomous surface ships, which will contribute to solving the issue of crew shortages and reducing human errors. The DFAS project just successfully carried out by the demonstration experiment using a domestic container ship between Tokyo Bay and Ise Bay, including a highly congested sea area in March this year. In this project, Fleet Operation Center, FOC, was constructed on shore. It consists of the integrated display block and emergency response block, and provides support by monitoring and analyzing the operational status of the ship. In emergency situations, the system can switch to remote operation to ensure the overall system safety. This research conducted throughout the DFAS project mainly has two objectives. First, to apply MBSE to autonomous navigation system development. Model-based systems engineering, MBSE, can consider overall requirements and function based on the purpose and goal of the system and provide a common understanding of the system with multiple stakeholders. At the first stage of MBSE, concept of operations, so-called CONOPS, is used to communicate overall system characteristics to the stakeholders. In this research, a reference model of CONOPS for crewless autonomous navigation system is concretized using DFAS systems as an example. The second is to establish safety evaluation method for autonomous navigation systems. It is important to know how to deal with emergent hazardous events in designing complex systems using new technologies. The hazardous control actions of the entire system was determined by STPA, System Theoretic Process Analysis, and the safety requirements for the system has been determined. This paper discusses how safety analysis can function in parallel with the autonomous ship design process. This figure shows the holistic view of the focus of this research. DFAS project conducted the whole process of this V model by utilizing software in the loop and hardware in the loop test. But in this paper, we focus on the design phase of the system development process, the left side of the V model. First, we develop a concept of operation reference model, and based on it, we demonstrated safety requirements definition scheme by STPA for detailed design. So how do we develop concept of operations? Based on the literature review, the elements necessary for CONOPS for autonomous navigation systems has been determined. In addition to the system's requirements, function, components, it is necessary to consider the system's background, purpose, use cases, and external environment and constraints, and the risk and impact of the system. The concept of operation for the DFAS system was outlined based on the contents in this table. In this presentation, I'd like to pick up and describe content number 3 and 4. First, conventional ship navigation can be divided into several tasks. In the case of autonomous navigation, some tasks would, in effect, be processed continuously by the computer, making it difficult to distinguish between them. Therefore, the function group is redefined as shown in the left. As it's difficult to navigate a vessel if the roles of man and machine are firmly fixed, it is required to have a system status management function that can appropriately judge the system status based on the information obtained. The system structure to achieve these functions was defined at the subsystem level, as shown in the right figure. Each subsystem mostly corresponds to the basic functions. For example, Central Information Management System, CIM, corresponds to the system status management function. Next is operational environment and scenario. This section describes the environment surrounding the system, including the use cases, related stakeholders, and data exchanged inside and outside the system. As for use cases, birth-to-birth operation is assumed in the nominal case, while remote operation from shore and emergency operation to ensure minimum risk condition are assumed in the off-nominal case. Since there are various navigational patterns for birth-to-birth operations, the modes of operation have been defined. In addition, the degree to which humans should contribute varies depending on the internal and external environment. Here, the 4 levels of status are defined: normal, active monitoring, remote fallback, and independent fallback. The status is determined by the CIM subsystem, mainly by the health level of maneuvering, propulsion, and communication subsystems. After developing initial CONOPS, SDPA is conducted, which can help us extracting safety requirements for the design. As a first step of SDPA, the accidents and hazards of the system and the safety constraints are defined. In general, safety constraints seem to be defined as close to the final consequences as possible. However, in considering a complex system, it seems difficult to extract the unsafe control actions with abstract safety constraints, as some control action can be too far from the consequences. Therefore, a chain of events has been assumed, and these intermediate events were defined as the safety constraints. After that, we extracted the unsafe control action by checking the interfaces among the subsystems described in the control structure one by one. At the first stage, we use system structure described in CONOPS. The 4 guiding sentences shown here are used as guiding sentences. Based on these, the unsafe control actions were extracted, and a couple of them are shown in the table below. The square brackets indicate the safety constraints that conflict. As a final step of SDPA, the hazard contribution factors were extracted for each UCA. The obtained UCAs and hazard contribution factors were organized in bow-tie model to increase their visibility. The countermeasures against the hazard contribution factors function as the requirements for the subsystems. Referring the framework of SysML, we organized the model diagrams of the system and clarified the relationship among them based on the safety requirements from SDPA. System configuration, including the modules and components in subsystem, was also detailed. In the real development process, SDPAs were conducted at several levels of granularity to design the behavior and structure step by step. Here is the summary of this research. We studied the appropriate CONOPS elements for the autonomous navigation system and designed a set of function and subsystems, and a new type of subsystem concept is proposed to manage the system status. We established a method using SDPA step by step according to the actual system development phase to extract appropriate safety requirements. We also proposed a set of safety constraints for the autonomous navigation system. As a future work, we will consider safety augmentation methods for autonomous vessels and simulation systems with scenarios to realize model-based validation and verification. Thank you very much for your kind listening.
Thank you. Okay, Takuya, thank you very much for a very in-depth presentation. I think it's very, very thoughtful, and do you have a paper as well? Yeah, I look
Yes.
forward to reading the paper to capture some of those details that went by a little bit fast. So do we have questions? Everything 100% clear? So you mentioned, if I could have one question, you mentioned the sea voyage that took place from Tokyo to someplace. And what were the learnings from that exercise?
Yeah, thank you very much. Well, actually, currently, it's for me, I'm currently in Boston, so I unfortunately I couldn't ride on that demonstration voyage, but so basically, the Tokyo Bay is one of the most congested sea area, and we can we could we could navigate the ship unmanned, I mean full autonomously, and that would be the big achievement, I guess. And yeah, so sorry about that, but I just yeah, we are now considering what can be what is the lesson learned, and also we have to seek for other points to be developed currently.
Right, so that's a very good segue to my next question, which is what are the next steps in this development?
I see. So we're in this paper, I just mentioned about the methodology for the design, but actually we also conducted some verification and validation by using the hardware in the loop test. But actually we are in the future, we are going to consider the model in the loop test as well. And well, we are gonna conduct the front loading at the model-based systems engineering process. And also we are going to conduct the safety case to argue its safety as well. So these are the next steps, I guess.
Okay, great. Thank you very much. Then if there are no more questions, I think we can move on. Thank you.
Thank you very much.